Okay. Hello, everyone. Welcome to today's TED Colloquium. We are lucky to have Jens Jasche from Stockholm University join us today. Jens got his undergrad degree in physics at University of Hanover and then his PhD at LMU in Munich in 2010. After postdoctoral fellowships in Bonn, Paris, and Munich, he has been associate professor at Stockholm for several years now. Pushing forward in cosmological modeling and data science. And you'll hear about his work in his talk now. He offered to answer questions as he goes along, so feel free to raise your hand and we'll stop him during slide transitions. Also, if you would like to ask questions semi-anonymously, you can always write to me in the chat and I will ask them without naming your name at the appropriate time. So with that, welcome again, Jens.
Yes.
And let's get started.
Yeah, thank you very much. First of all, I think I'm going to copy the link to my presentation into the chat. So in case there's some lag, you can follow it, or you want to have another pace going through my presentation. Here it is. Let me know if this works. And then I'm going to share my screen. And okay, can you see my slides? Excellent. Okay, so thanks, Elisabeth, for the kind introduction. It's a real great pleasure to be able to present our work on Bayesian forward modeling of cosmic structures and galaxy surveys today. This is actually ongoing work which I'm conducting in collaboration with a large group of people, and most notably here is Guillaume Lavaux, Adam Andrews, Florent Leclerc, Natalia Porqueres, Dugesh Kodi Ramana, and many, many more people who are members of the Aquila Consortium. So the Aquila Consortium is an international research collaboration, and we are interested in developing and applying novel data science and machine learning techniques to study the three-dimensional spatial distribution of dark matter underlying observed galaxies in redshift surveys. And we are interested in doing so because by studying the three-dimensional distribution of matter in surveys, we hope to learn about the fundamental physical processes that govern the dynamics of our universe. And we also attempt to go beyond standard cosmological analyses, which basically try to summarize the dark matter distribution in terms of statistical summaries by basically providing a characterization of the full three-dimensional dark matter distribution and its dynamics from data. So the work that we are doing on a daily basis is very technical. So we are developing a lot of algorithms and coding and so on. I decided not to go into any of these technical details here today and rather provide you with a high-level conceptual overview about what we try to achieve and our motivation for this work. Actually, as we speak, this week, we have one of our biannual meetings from the Aquila Consortium, so there's lots of action going on. Right now, a lot of people are working on projects. I picked some of those projects which are actually ongoing work and will present it later, just to give you an overview about the things that we are doing. As Elisabeth said, please, if you have questions, interrupt me and ask questions directly. I also have a tendency to speak very fast. It goes fast through my presentations during these remote meetings. So slow me down if you would require this. So just allow me to give you a very brief motivation for what we try to achieve and why. We want to learn from data the physical conditions of our universe. And whenever you want to try to learn something from data, what you actually need, first of all, is you need to have a hypothesis or model prediction that you can test against observations. And in cosmology, different to many other fields of research, we are in a very comfortable situation that we have an excellent theory framework from which we can derive models and then hypotheses and model predictions that we can test against the data. And in cosmology, our theory framework is basically determined by gravity. So we believe that the dominant force in the universe is gravity, indicated by Einstein's field equation as shown here, and close by the Bianchi identity. And you can think of this gravitational equation here as a set of coupled second order differential equations. So we basically have to solve either these equations directly or approximations thereof to arrive at model predictions that we can test against data. And that's actually very interesting because you can just look at these equations and directly read off the major core questions that we have about cosmology these days. And the first question is, what is gravity? So our theory picture of gravity, is it correct? The second question that we have is, what is the content of the universe? What are the sources of gravity? Is there dark matter and dark energy, for instance? And finally, what we actually need in order to arrive at model predictions, we need to set the initial conditions for these differential equations and evaluate the dynamics of the universe. And that turns into the question of what are the initial conditions of the universe. And this is related to early universe physics, the origin of cosmic structure, Big Bang, and so on. So it's basically all the questions that we can have revolve around these gravitational dynamics in cosmology. And we can now make some fundamental assumptions. We can postulate something. We can postulate that Einstein theory is correct. We can also postulate that the universe is, for instance, filled with dark matter and dark energy. And we can further postulate that the origin of structure were generated during an early epoch of inflation, which generated quantum fluctuations, which form the seeds of the cosmic structure roughly 13.8 billion years ago. And if we postulate these things, then we arrive at the standard model of cosmology. And this leaves us with a highly predictive model that we can actually use to test these model predictions against observations. Just to remind you, these standard cosmological model basically predicts that all observable structures in the universe arose from tiny primordial quantum fluctuations roughly 13.8 billion years ago. And whereas in the initial universe, we had an almost homogeneous meta distribution, in the course of roughly 13.8 billion years of cosmic history, these seed fluctuations grew via gravitational amplifications to form a filamentary cosmic web, as can be seen here in this right slide, which is a presentation of our present dark matter distribution in the present universe. And you can see that it's a highly filamentary structures. We have clusters, huge empty regions, the so-called voids. And the important thing to realize is here that the specific configuration and shapes of these three-dimensional structures, they retain a memory on the initial conditions, but basically on all physical processes that led to its formation. So in order to learn about the universe, we can basically try to study the three-dimensional large-scale structure in cosmological observations. That is, of course, hampered due to a lot of observational effects like noise, systematic effects. I don't want to talk about that at this instance, but I'm going to talk about this a little bit later. But the problem starts already earlier, because if we want to understand and study the nonlinear large-scale structure in its full generality, we need to develop likelihood distributions and posterior distributions that can account for the full statistical characteristica of this characteristics of this density field. And unfortunately, there is no closed form description of a multivariate probability distribution that can describe the statistics of the dark matter distribution to the degree that we can actually use it to build our posterior distributions and likelihood functions that we would need to develop a statistical inference machinery. That is very unfortunate, and that is also the reason why traditionally in cosmology we study the cosmic large-scale structure by basically summarizing summary statistics of it. So one of the most prominent statistics that we use is the two-point statistics, or as shown here in the right panel, the cosmological power spectrum, which is the Fourier transform of the correlation function. And it contains interesting cosmological information, but it is not a full description, or it doesn't contain the full information of the nonlinear density field. And just to illustrate you, to give you an impression about what kind of information is lacking from the statistics, I show you here in the left panel a evolution of a cosmological dark matter density field in a simplified structure formation model. We start from roughly redshift 25, where the initial density field is still fairly Gaussian. And you see that it's in the course of structure formation actually forms filamentary structures in a highly detailed and structured field. In the middle panel, I show you a field which has exactly the same two-point statistics as the left one. And you can see already for the experts, this is exactly the same field, but with scrambled phases. And so this middle panel field only contains the information of the power spectrum. As you can see in the right panel, the blue and orange curve, they are exactly identical. So both fields have exactly the same two-point statistics. But when you look at it, especially at later times, they look visually very, very different. And you can definitely see that the middle panel does not contain the same information on the detailed large-scale structure as the left one. So by actually limiting ourselves to statistical summaries of the density field, we are not able to capture all the details of the cosmic large-scale structure. The natural attempt that one could do right now, and what is the current state and attempt, is to increase the number of statistical summaries that we are using, either 3x2 PT or going to higher order statistics. But eventually, this description of the dark matter density field in terms of summary statistics is not guaranteed to provide the full information content of the large-scale structure, as even an infinite hierarchy of higher order moments of the density field is not guaranteed to close. So what could we do? That was a question that we actually tried to look with a fresh view in 2014, when I was in Paris studying with Ben Wandelt. And so what we decided is to just make a step backward. So we just wanted to know, okay, what is the origin of the statistical complexity of the nonlinear density field if we look here at this right panel, whereas we know from observations and from theory that the cosmic initial conditions, roughly 13.8 billion years ago, are very close to a Gaussian random field. So while the initial conditions are statistically almost trivial, the final density field is statistically very complex and very, very difficult to handle in statistical terms. But if you step back and ask the question, where does it come from, then you realize that it is basically just a transformation via deterministic gravitational processes that transform the initial density field, the initial Gaussian random field, into something that has apparently a higher statistical complexity. But since both fields here are related via deterministic processes, it is just a transformation for the statistician. It is just a coordinate transform or a change of variable from this field to this field. Yeah, so it's an apparent statistical complexity, both fields, if gravity is exactly deterministic, have exactly the same information content. It's just that the final density field looks more complex. So the question then arises, if the final density field is statistically very complex to model, and the initial density field is statistically much, much more trivial, and both fields are related via deterministic gravitational processes that we know how to model, that we can handle through either approximate structure formation models or full n-body simulations, then why don't we try to turn the problem of analyzing the cosmic large-scale structure in the present universe into an initial conditions problem, where we try to infer the initial conditions from which the present observations actually formed. So we try to turn large-scale structure inference into a large-scale initial conditions problem. And that is an idea which is actually not at all that new. So last year we celebrated here in Stockholm the Physics Nobel Prize, and Peebles got it. And one of his works, actually already fairly early, dealt with trying to reconstruct the initial conditions for the galaxy motion in the local universe. So he basically measured the velocities of galaxies, or he took measurements of the velocities of galaxies in the nearby universe, and then he tried to reconstruct the initial conditions, the initial positions and velocities from this one. And he then basically used an n-body simulation to forward evaluate this system of galaxies and to arrive at the predictions of velocity. And it's actually very interesting to realize that back then with his method, he already produced or predicted a low mass universe. So you can see that this idea of actually taking the physics serious and trying to fit the physics directly to the observations is a quite old one. It's a technically challenging, complex one. But it's a very fruitful approach. So what we have done in 2014 is we wanted to take this approach to the next level and implement this basically into a full Bayesian framework. So we wanted to develop a complete posterior distribution which can perform such an analysis by analyzing the three-dimensional galaxy distribution. And we do this by starting out from a Gaussian prior in the signal S. S in this case is actually the initial conditions, so the initial state of the universe. We assume it here to be a Gaussian distribution because we know from theory and observation that it should be very close to a Gaussian distribution. I will show you later that we can relax this assumption and account for the very, very mild non-Gaussianities which arise due to inflation. I will show you this toward the end of my presentation. So the idea is the following. We basically start out from a random realization of a cosmic initial density field. We then use our favorite cosmology simulator, maybe a particle mesh code, which solves this equation of motions here for a set of particles and translates the initial density field into a nonlinear density field. The corresponding probability distribution that basically translates our initial conditions S to the present delta density field delta is basically a Dirac delta distribution where G is our gravity model simulator, which translates the signal S into the simulator output, which is basically a density field like this. And you can then take the model prediction here, and you can basically use various recipes to populate it with galaxies, and then you perform a virtual observation of this one. So you try to emulate a mock data set that looks as close to the real observations as possible. We typically assume, for simplicity, a Poisson likelihood model, which has an intensity function which is related to the density through a parameterized bias model. This is just an example here. We have all kinds of different likelihoods that we can use, and we are exploring a broad range of different biasing strategies ranging from EFT calculations to neural network strategies to try to emulate the galaxy formation process. I will not go into many of these details here today, but in principle, you can exchange this with any kind of data model that you want. The machine is sufficiently flexible to do this. So you take so the machinery works like that. So you sort out from a Gaussian initial conditions, you run your favorite simulator, you make a model prediction. And what you now would like to have is, when you compare two observations, you would like to take this data misfit and propagate it back to the initial conditions. So what we actually would like to do is, we would like to follow this approach here. We start out by setting initial conditions. We use our favorite physics model to simulate the gravitational growth. We take this model prediction to simulate artificial data, and we compare this to actually observed galaxy data then. And then we modify our initial hypotheses, update the initial conditions, and we iterate this. In practice, what we are doing is we run a very high dimensional Markov-Chain Monte Carlo algorithm. So the idea is that the posterior distribution that I showed you before needs to be explored via a Markov-Chain Monte Carlo algorithm. And you guessed correctly, this involves running a n-body simulation at every step in this Markov-Chain Monte Carlo approach. And this is highly challenging numerically, but even more so because we are dealing with roughly 10 million dimensions, which are the density amplitudes of this initial density field that we try to fit. And so we are facing the curse of dimension. And that's non-trivial a problem to explore. One approach that we found to be working and still is probably one of the best approaches that you can use for these kind of problems is the Hamiltonian Monte Carlo approach, or HMC. And this HMC basically uses classical mechanics to solve statistical problems. Whereas traditional MCMC approaches basically perform a random walk in this high dimensional parameter space, which basically would never come to a conclusion because this sampler would run in circles. The HMC suppresses this random walk behavior and permits us to actually run persistent motion in this high dimensional parameter space. I don't want to go into the technical details of the algorithm. I just want to give you an idea why it is actually working and why you can solve these high dimensional parameter space problems with that. And I start out by providing you a simple cooking recipe. So you have your probability distribution P of X, which you would like to explore. And you just interpret the negative logarithm of this as a potential psi of X. And as physicists, what we do, if we have a potential, we basically add a kinetic energy term, which is quadratic in this case, in the momenta. And we have something which we call a mass matrix, which for the purpose of the algorithm is nothing else but just nuisance parameters. So by introducing these nuisance parameters, you don't change the statistics of the original problem. You can see this if you take the Hamiltonian, the negative Hamiltonian to the exponent, then you see that this distribution factorizes into a Gaussian distribution in the momenta times the original target distribution. And because the distribution factorizes, if you marginalize over the momenta, you get back your target distribution. So there's no problem in adding these additional parameters. It's a little bit counterintuitive to realize that basically by doubling the parameter space, by adding these nuisance parameters P, the problem becomes much, much easier to solve. And the reason for that is that we can basically now use Hamiltonian dynamics to explore the parameter space. So we can use these standard equations of motion for these meta statistical problem here. And you can think of this, we start out in this parameter space, in this augmented parameter space X and P. at some point, and then we evaluate these equations of motion for a certain amount of pseudo time, and we arrive at a new position x prime p prime. The very interesting thing right now is that the motion here is not a random walk. You can see that the forces here of this Hamiltonian equation, they depend on the gradients of your negative logarithm of the posterior distribution, and therefore the particles are actually following the forces, so they are attracted towards the relevant high density regions in the parameter space, and then they explore these regions via orbital motion. And to arrive at a full valid Markov chain Monte Carlo algorithm, what you basically do is you integrate these trajectories for a certain amount of pseudo time, and then you randomize the momenta. So the direction and the amplitude. So this means you heat and cool the system basically. You let it run for a certain amount of pseudo time, and then you accept the new point x prime according to the standard Metropolis Hastings rules, which is given here, which is the acceptance probability alpha, which is the minimum of the 1 and the exponent of the difference between the Hamiltonian at the final point and the initial point. And the brilliant thing that happens here right now is that Hamiltonian dynamics conserves the Hamiltonian. So we arrive at an acceptance rate of 1. And that is very relevant in high dimensions, because I told you that we basically need to run a Markov chain Monte Carlo algorithm where in each step we run a full-blown n-body simulation. So a high rejection rate would render this entire business completely futile. So in practice, we don't achieve an acceptance rate of 1 because there's, of course, numerical errors in the integration of these trajectories here, but we are typically larger than 68 to 80%. That's the acceptance rates that we have for our problem. So the HMC helps or addresses the problem of the curse of dimensionality, first by using gradient information to really move into preferred directions in this high dimensional parameter space. And second of all, using conserved quantities like the Hamiltonian energy conservation to have an efficient parameter space exploration. So that now brings us in a very excellent position, because now we can include these large-scale structure initial conditions problem into a general Markov chain Monte Carlo framework. So we have designed the Borg algorithm, which stands for Bayesian origin reconstruction from galaxies, as a modular statistical programming engine. And this one uses basically hierarchical base and block sampling, which allows us to build very flexible data models. What you can see, for instance, here is that we can, in a Lego block fashion, add different blocks to the sampler, which here the large-scale structure sampling approach, which provides us with the initial conditions, velocities, and nonlinear density fields, can be combined with different models of bias parameters, noise models. We can sample the observer's velocity. We'll show you later that we can add samplers for systematic effects in the data that are unknown, cosmological parameters, and so on. So by being able to formulate this as a Markov chain, we now have a very, very flexible modeling engine that allows us to solve very complex inference tasks of the cosmology. What I want to show you, and I hope you can see this here, maybe let me increase the quality a bit. What you basically see here are now the results of this Markov chain. So the sampler now moves through this parameter space and tries to identify large-scale structure configurations that are compatible with the observed galaxies. What I would like you to see here is that on the right panel, you see the galaxy distribution. That's galaxies of the 2m++ galaxy compilation in the actual universe. So this is real data. And in the left in the left and in the middle panel, you see the simultaneously constrained primordial density field and the present large-scale structure. So if you focus for time being on the middle panel, then what you can see is that where we have a lot of data, the large-scale structure is very well constrained. It doesn't move a lot. Yeah? And that is because we have a high signal-to-noise region there. That is where we can reliably reconstruct the cosmic large-scale structure. But in regions where we have no data or very sparsely sampled data, you see that the large-scale structure moves quite a lot. So the algorithm now tries to explore three-dimensional large-scale structure configurations that are compatible with the observations. And basically what you can see here is Bayesian statistics in its purest form. That is a numerical representation of the posterior distribution. And that's basically what you can get if you apply Bayesian statistics to incomplete and noisy data. So that is basically what the algorithm does. It explores this high-dimensional parameter spaces of the initial conditions and the present large-scale structure. And we can use it now to perform a variety of analyses. So I would like you to show some of the results that we have obtained by applying this algorithm now to real data of the nearby universe. We are constantly updating the algorithm and exploring different data sets. So this one is already quite old data. It's from last year. We constantly update this. But this is the result that we obtain if we apply the algorithm to the galaxy data. So that's the degree of detail that you can expect to reconstruct the large-scale structure. The red dots, these are the actual galaxies in the 2M++ galaxy survey around us. The dark structure in the background, this is the actual reconstruction of the dark matter distribution. And you can see that the galaxies nicely trace the underlying dark matter structure in the survey. So we also get the initial conditions. That is this one here. So that's basically the initial conditions from which the present universe structure has formed. And just to show you, maybe to give you an illustration that this really fits, you can have a look at this regions or any other region in the sky, and you will see that there's a correspondence between the structures there. So you can really see that we reconstructed the initial conditions, the three-dimensional spatial initial conditions, which can explain the present observation in the present universe. We get a lot of information. We get dynamical information. Basically, you can think of, we get all the kind of information that you also would get from a standard n-body simulation, the kinematics, and so on. There's a lot of things that we can do with that. I just want to show you, here's another map, again, to show you this is a degree of detail that we aim to reconstruct. So you see that the reconstruction that we obtain these days are very close to what you can see in n-body simulation. A couple of years ago, reconstructions, meta reconstructions were not that detailed as we have right now. And I would just like to focus on this little red region here, that is the famous Coma Cluster region. Sorry. And we can zoom in, and that's basically the Coma Cluster as it appears on in the projection. So you basically see that Coma Cluster forms along various filaments here. Actually, there are 5 filaments along which mass accretes onto the cluster. What we can do is we can not only study the velocity fields and the dark matter distribution of the cluster, but we can actually use our reconstruction to follow the entire dynamical formation history of the Coma Cluster. And what I want to show you next is basically we try to rewind the time and show how the Coma Cluster formed. I did a very simple plot. Oh, sorry. So let's have a look at the upper left structure. There are 3 structures, A, B, and C. These are 3 proto-structures which I identified Right now we are moving backwards in time, so the things are moving apart. Now we are moving forward in time, and you can down here, you can see the cartoon, and you can basically see there's a merger right now, there's another merger right now. So you see that there's a lot of dynamics. What you can also see, if you look down here, you can actually see that there's orbital motion. So you see that this is not a linear reconstruction, but that you have really nonlinear dynamics in the reconstruction. So again, this is only one of these realizations that we have. We typically explore the posterior distributions. We have typically 100,000 of these realizations. So we get 100,000 plausible of these large-scale structure formation. One of the very nice things is that we get the merger history that we get, that we have these two mergers, and the latest one is fairly recent. We get this quite consistently in all these plausible formation structures, and that's also in agreement with the observations, because then we know that Coma from radio observations, that it's a shock cluster, and there must have been a recent merger. And it's nice that this is a plausible explanation that fits with those things. I want to convince you that this formation history is not just a random thing, but that it actually makes sense. So what we did is we actually tried to measure the radial mass profile around the Coma cluster. And that is actually our curve here. So the red solid curve is our measurement, which we get from our reconstructions. The light gray and dark gray shaded regions are the 1 and 2 sigma confidence regions. And we also compared to weak lensing and X-ray measurements that we got from the cluster. So here's a list of literature, and we compared with this, and you see that we are nicely in agreement with these measurements on scales of a few megaparsecs. So that's very nice. So apparently we are able to use the dynamics of the system to reconstruct the mass. We have not been lucky with the Coma cluster. This is the Virgo mass profile. You see that's one measurement that we found there, and that's the Shapley mass profile. So you see also that our reconstructions, which are the continuous lines, are very nicely in agreement with complementary measurements in the literature. So the nice thing right now is that I basically showed you that we have a very detailed reconstruction of the large-scale structure, which agrees with the overall structure of the galaxy distribution. So we have something that is spatially in agreement with the galaxy distribution. So the mass is at the right spots. And when we look at individual structures, then we also see that the actual amount of mass that is in this region agrees very well with complementary measurements. And that lets us believe that we have a very good reconstruction of the dark matter distribution in the nearby universe that actually surrounds us. That, of course, is still something of investigation, but so far, this looks very promising. Here's another thing, that's a Virgo cluster, just to show you in the degree of detail that we get and what you can do, kind of studies. You can basically think of doing all kinds of studies that you would typically do with an n-body simulation, but here you get simulation, or you get actual data, you get information from actual structures. And here you can see again that there is filaments of mass which accretes onto the Virgo cluster and so on. Here's another project actually from a student and from Isabel Tanzeri, just a very quick project. She actually studied the filament distribution in the nearby universe by using the disperse filament finder and just identified the filaments in the reconstructions. Just one project that you can do, it's preliminary work. You can then basically try to measure the radial profiles, mass profiles of these filaments of different length size. The important thing, this is preliminary work, what we have found is that there's a simple linear log relation as a function of the radii from the filament center. So this is preliminary work. And another thing that we were interested in looking at is the filaments are not straight lines, but they're slightly bent. And we had a look at this bending angle, which we measured from the filaments. And it's really interesting, but we have no explanation for this, so take this with a grain of salt. The peak here is roughly at 137 degrees, and that's roughly the golden angle, so that's a Fibonacci series. Whether or not this has something to do with the hierarchy of structure formation, that's something, it's just a curious number. Maybe it's just a coincidence, but this is the kind of information or test that you could do also with the things which we want to further investigate. Another thing that is very interesting to us is that we can get dynamic information. What you see here in this plot is a plot of the radial velocity, because we basically have fit the n-body simulation to the data. We have all the kinetic information of the mass in the nearby universe. And basically you can see that the blue stuff, the blue regions, they are moving towards us. The red regions, they are actually moving away from us. And very interestingly, you can see that in between there are regions of these yellowish color. That's basically where the line of sight velocity changes the sign or is exactly 0. And these are regions which are in Hubble flow. And that's particularly relevant in the nearby universe, because if we want to measure Hubble nearby, then we have to account for these peculiar velocities. Another thing that we could do for the first time is, because we actually fitted in particle mesh codes on n-body simulation to this one, is we could have a look at the vorticity field of the velocity field. So we could look if there are deviations or how non-potential flows would behave in the nearby universe. And what you can see here is the amplitude of the vorticity of the velocity field. And you can basically see that it nicely traces the filamentary structure in the nearby universe. These clusters here, there's Perseus Piscis, and this here is the Virgo concentration. So you can really see what kind of information you can get by fitting this dynamic information to the large scale, to the data. Another thing here, just to show you, this is just a visual impression. It's a slice roughly 25 megaparsecs around us, just showing you that's the Hubble fraction error due to the peculiar velocities. So you see that if we're in the nearby universe, the Hubble error on the sky is not homogeneously distributed, but there are preferred regions which either move away or come towards us. So this is something that one needs to account for if we want to measure Hubble in the nearby universe. And that is actually a work which we have done last year, where we basically wanted to know for this one gravitational wave, GW 170817, how much does peculiar velocity impact the measurement of the Hubble parameter. And you can see this colored map in the background. That's our mass, our velocity reconstruction. You see this is the position of GW 170817. And when we do the analysis and we do our H0 measurements for this single event, then we get basically a correction of roughly 10%. This is also in agreement with other work that has been done there. The 10% correction is what you typically can expect, but this is crucial because over the next 5 to 10 years, there's the attempt to actually bring down H0 measurements to the 2% level accuracy, and that's then actually where in the nearby universe, and that's actually then where you have to account for peculiar velocity. So this is becoming more and more important for as data becomes more powerful. So that's it for the nearby universe. I want to show you that we also now extend to deeper surveys. The big surveys are coming, Euclid, LSST, and we are involved in those as well. So we are preparing the machinery to go deeper. And I want to show you an application to the Sloan Digital Sky Survey 3, data release 12. So we look at redshifts now smaller than 0.7. And the first thing that happened when we tried to apply our Borg algorithm to the SDSS data, that's what we got. So the red curve is a fiducial cosmological power spectrum, and the black dots that you see here, that's a reconstruction that we got from Borg. And you see this huge erroneous large-scale power that we get here. And that is not a trivial thing, because we fit the entire dynamics model to the large-scale structure. And so this can largely invalidate the reconstructions, because this affects all the peculiar velocities, the displacements, and so on. So this is a huge nuisance when trying to deal with these kind of surveys. We are not the only ones, actually. You can look into the literature, and there you can find that this is typically found in other measurements of the power spectra as well. And these effects are known, and they are known due to all kinds of foreground contaminations that you can expect in these surveys. For instance, you can have dust, you can have the PSF widths, you can have stellar contaminations. There's a paper by Boris Leistet and Irania Perez from 2014 where there's lots of maps in there, and there are many more than this, and you have to account for this. So we accounted for this already. So we can introduce these foreground template sampling into the machinery of Borg and account for this, but that was not enough. So there seemed to be some contaminations in the data that could not have been sufficiently modeled by the set of templates that we used. And so we gave up at some point in trying to model this explicitly. And so we said we wanted to have a robust approach. So we want Borg to basically explore what kind of foreground contaminations could there be that we missed. And in order to do this, we basically provided it with a framework to be agnostic about it. So we basically said, okay, you can have this potential map of foregrounds. We leave every pixel of this foreground map, we leave it free. It's a free degree of freedom, and we fit it jointly with the data. If you take the 2D map and you extrude it into 3D, then you see that in 3D you get shapes like that. So it's really irregular volume elements which you get by extruding this. So it's challenging. You can do this. And luckily, if you work out the mass, you find out that you can marginalize over the foreground contaminations, which are called A here. So the amplitudes of these unknown amplitudes of this map. And you arrive at a very simple equation, which is basically just the ratio of the Poisson intensity divided by the sum of all Poisson intensity in one of these patches. And this makes it very robust against all kinds of foreground contaminations on the scale of these maps. And the algorithm can basically deal with that. And that's actually what happens then. So if we did this, we get the large scale power spectrum correctly. This again is a map of the dark matter distribution in the SDSS3 survey. So you see that it actually works. So we wanted to test whether this works, if the large scale reconstruction actually makes sense. So we did a simple cross correlation between the predicted kappa map or convergence map of Borg with the Planck 18 map. And that is the result. If we just do a very simple cross test, then you see that the Planck 18 and the Borg convergence map have a very great alignment. So the large scale modes that we actually reconstructed, they are actually in agreement with a complementary data set. So this is very encouraging that this procedure actually worked with real data. There's another thing that we can do now. We can actually use the physics model to inform us about what would have been these systematics. And that is what Borg can do. It can provide these maps of unknown foreground contaminations a posteriori, after the fact. And for instance, if you look here at the right panel, the second from the top, then you see that there are these striping features. And these are definitely not of natural origin. We actually don't know what it is. One needs to have some follow-up investigation of this, but this is a demonstration that the algorithm can actually inform you about artifacts in the data that it did not believe would be compatible with the physics picture. And that's very powerful because you can then start follow-up investigation and see if there's an artifact in your data which you have not been informed about before. We also move forward now to actually test cosmological parameters. That's a proof of concept project by Dugesh Kodi Ramana, who was interested in actually using the shape of the cosmic large-scale structure to constrain the cosmology. And in particular, according to the cosmological principle, we expect that cosmic structures should be spherical on average. And that is when we observe them in redshift space. On average, if we would use the correct transformation between the observed redshift space and co-moving distances, on average, these structures should appear spherical. They would appear elongated or squeezed if we use the wrong cosmological transformation between the redshift and the distance. And that's basically what you can see in this movie here. So it's basically a scan through the cosmological parameters, what happens to the large scale structure if you stretch it. So you really see that you can use this information, this pure geometric information, to test cosmology. So that's what you can do. You can basically implement this into this block sampling framework of Borg. You have the three-dimensional density sampler. You can use sample your galaxy number densities. You sample your cosmological parameters, your galaxy bias parameters, and you iterate all this together. And then you try to constrain the cosmological parameters, in this case, omega and W naught. That's the result on basically an SDSS mock catalog. You can see that we simultaneously infer the three-dimensional density field. And in the lower panels, you basically see the statistics for the inferred parameter omega meta and W naught. So we get a very, very precise measurement. And just to give you an idea, if you would just compare this to the standard BAO measurement, then without additional information, additional constraints from Planck, just BAO from the large scale structure, then you get the ellipse, the green ellipse. And if you use the Borg Altair model, which is Dugesh's Alcock-Pyczynski test model, then you get this little bluish ellipse. We roughly get a factor 10 improvement in significance in constraining these parameters. And that is simply due to the fact that we can basically use many, many, many more samples per volume element. If you use the BAOs, then you have one sample every 150 megaparsecs. But now, since we can go to smaller elements, smaller scales, we sample our large scale structure in this test at roughly 15 megaparsecs. So we have many, many more samples per volume element that we can use to perform the cosmology test. And just the counting of scales already accounts for a large fraction of this information. There's another nice thing that we constrain everything together. The model parameters, the bias parameters, all kinds of data model parameters. So you see there's a huge number of parameters that we have, and there's only these upper two here. These are the cosmological parameters, W naught and omega meta. So, and that is a correlation structure between all those parameters. What's nice that you can see is that the correlation between the cosmological parameters and the bias parameters is very weak. So that's because it's a geometric probe. It does not care so much about the density amplitude. It cares about the shape. And that is nicely represented here. I think I will skip this slide here. I want to move on to the next one. That's a project by Adam Andrews, a student of mine, and he's interested actually in doing something that is really natural, using this inference technique to study the origin of cosmic structure. So what we want to study now is we want to actually study a primordial non-Gaussianity, which is predicted by the theory of inflation. And we want to use the Borg algorithm to reconstruct the initial conditions. And you can see that this can be easily implemented into this forward framework. So we start with the initial density field. We use this model here, which is standard model to generate the local type of primordial non-Gaussianity in this. So we feed this physics model into the initial conditions process. We run a forward model. We generate the galaxy biasing, which can account for scale-dependent galaxy bias due to the formation with FNL models. And we add all the systematics and we arrive at a catalog. So by fitting the entire three-dimensional large-scale structure, we try to simultaneously account for a variety of effects in the large-scale structure that you can use to actually constrain this primordial non-Gaussianity parameter. And that's first of all the higher order statistics, the skewness of the galaxy distribution. We have the large-scale velocity fields and redshift space distortions that we can account for. We use light cone effects, we handle this. You can use the cluster mass distribution, void sizes, the entire topology of the large-scale structure and the scale-dependent galaxy bias, which is implicitly accounted for through the forward modeling of the physical forward modeling of the field. And just to give you an idea here, a visual impression of this one, the left panel is a panel where you have an FNL, an exaggerated value of 250. In the middle panel, you have FNL of equal 0. So by eye, you see very little difference. But if you take the diff of that, then you see which regions in the large scale structure would be affected by different FNL. So you can see that we are not really trying to fit the different summary statistics, but we really try to identify these misfits in the data and use this to constrain the FNL. This is again the pipeline, so you can build it up into this Markov chain Monte Carlo framework. We sample the initial conditions, we have the physics forward model, we use the likelihood, we sample the FNL parameter, and we iterate this entire Markov chain to sample the cosmological parameter. And we can use all kinds of models, so we can update our model for primordial non-Gaussianity straightforwardly as you would do in a standard n-body simulation, and then fit the new model against data. This is one of our preliminary results where we did a simple test of a Euclid-like survey. It's a very simplified one. We have an equivalent of roughly 50 million spectroscopic galaxies in a 5.7 gigaparsec box. It's roughly a Euclid volume. And we chose for this mock a true FNL value of 5. Here in the upper panel, you see a trace plot of our Markov chain. And in the lower panel, you see basically the histogram of the FNL parameter. The blue curve, the black one line here, that's actually the true value. And the blue is the ensemble mean estimated from the Markov chain. And you basically see that we get back the FNL with a sigma plus minus 0.61. So we can actually reach the science target. Again, we have cross correlations between all the model parameters and the FNL parameter. That's what we get. So we can do detailed statistical summaries. And I think what I wanted to show you here today is that what we try to do is actually we try to build a plausible model of our universe that actually tries to go beyond the traditional approaches of just measuring statistical summaries by trying to build a plausible three-dimensional model and that describes the formation of the large-scale structure from the origin to the present to the degree that it is actually corresponding to the actual universe on an object-by-object basis. And I think I want to summarize here. So this is ongoing work. This is still very early work, but we have hopefully demonstrated that there's a new approach to analyzing cosmic large-scale structure that can bypass the traditional approach of just measuring the statistical summaries by just straightforwardly fitting the physics model to the data in its full generality. So we have demonstrated in various successful pilot studies that we can get relevant and interesting results. And for instance, we can also deal with effects in the data because the physics informed model can help us to break degeneracies or identify unknown data contamination. So scientific results are a very nice characterization of the cosmic initial conditions in 3D, not only statistical, but also, of course, we are now starting to investigate the primordial early universe physics. We have accurate and detailed reconstructions of the dark matter density field. We can access the dynamics of this dark matter distribution and perform dynamical mass reconstructions. And we are now pushing it towards constraining cosmological parameters. And the first tests that we have, of course, need to be further tested, but they look very promising. So as I said, the Aquila Consortium meeting is going on these days. So if you have more questions or curious about projects, then please follow us at our webpage. We are pushing forwards to other projects. We are including weak lensing right now, peculiar velocity data. We try to deal with photo Z. So there's lots of things going on. Thanks.
Thank you, Jens, for that impressive grand tour. Fascinating. I'm sure there will be many questions. Jasche, do you want to start?
Yeah, sure. Thank you for very great talks. I noted that you sort of doing a test on the CMB lensing. Have you ever predicted the CMB power spectrum from the reconstructed initial conditions, or could the Brock helps on resolving sort of the tensions of the early universe and the late one?
So I'm not sure if I get this. So of course we can measure the cosmological power spectrum from the initial conditions, and that one looks okay, if that's what you mean. And other than that, I mean, we can cross-correlate all large-scale structure data, but that's basically secondary anisotropies with the CMB. I'm not sure if I'm answering your question.
Because like there seems to be tensions about the parameters measured from the CMB and the late universe.
Ah, okay. So H0 tension, sigma 8, and so on. That's what you refer to.
Yeah.
So in the reconstruction that I showed you, we didn't do a cosmological parameter analysis. So from that aspect, it's really difficult to say if there's a real tension in our reconstructions. We are moving towards this direction yet. We have no cosmological parameter constraint yet that is really showing a that we could use to see if there's a tension or not. So what we have used is we have used our peculiar velocity reconstructions to see if they can, for instance, remove the tension in the H0 measurement of nearby objects with the CMB measurements. They can explain a part of it, but not everything. So, and the tension seems to increase. So we have to look more carefully in it. I don't believe that peculiar velocities are the sole explanation of this. So that's the degree of test that we have done.
Okay, Eduardo, I think you have another question.
Yeah, well, so I had a couple questions. One question was related to which was, there's been all this talk about using K equality as a standard ruler, but there's been a couple of papers on that. So I was going to ask whether you guys had looked at that at all. But it sounds like you're just in the middle of doing it.
Yeah.
So that's awesome. I guess a second question would be, how are you doing? How are you doing RSD modeling? Like particularly, like how do you handle like things like satellite galaxies and and things like that for the purposes of doing that distance to redshift mapping?
Okay. So at this moment, it's very crude. We are not to that level yet. So we basically get peculiar velocities on some coarser level and on some large scales from the physics model. Let's say on 2 megaparsec scales or so, we get the peculiar velocity field from the physics forward model, and then we typically add an additional dispersion to this to account for the visualization, and we fit the dispersion parameter typically. So, but it's a phenomenological model at this moment, which basically just accounts that basically says that we are not able to fit the model to the small scales. So this basically then just accounts statistically for the additional uncertainty. So there are lots of people working on this right now, what to do. There is various approaches in this direction, either trying to model this along the phenomenological road or trying to solve this with neural networks training and so on. So there's lots of work in progress, but which has not have a conclusion so far. So far, we take the peculiar velocities as resolved by the physics model, and then we add a dispersion that accounts basically says that we can't trust our model or the data to a certain accuracy.
Thank you. Awesome talk and awesome work. That's super cool.
Thanks.
Are there more questions? Eduardo, do you have another one? Give your hand raised.
Oh, I can ask another. I mean, I have lots of questions, so I can keep asking questions. But if other people have questions, I guess I'll ask one more question. I guess have you guys played with adding Halo Finder at the Halo finding and trying HOD type approaches to within the context of Borg? Is that reasonable, or like you run into trouble with the simulations because you need the simulations to be quick or something? This is just me like curious about next steps.
Yeah, so we have been thinking about this. So what we need for the HMC is we need basically that the model is differentiable. So basically we need to have the model prediction needs to be differentiable with respect to the initial conditions. Halo finding is a little bit nasty because it's not straightforward differentiable, because it basically turns your continuous field into discrete objects. There are ways to do this. I mean, people try to basically use neural networks, but I've recently looked into this, and I think you can actually find an algorithmic derivative of the Halo finder if you make some weak assumptions, so that you basically soften the switches that are in there. So you make them softer, and then you have a derivative of this one. Yes, so we are investigating this, but speed is crucial. And it seems that even though we might be able to do this, a neural network to the degree of accuracy that we can hope to deal with in real data in the end might be much faster. And since we have to do things very often, I think right now as it looks, neural networks will probably win the race. Yeah. What we have been looking into, and that's actually ongoing work, is to do this in post-processing. So we have these dark matter reconstructions, so then you can basically run a Halo finder on that and use an HOD to populate it. And then you can test with real data and see if it agrees or not. That's a project actually that we are doing with Harry Desmond from Oxford. So he's interested in doing this. Yeah, you can play a lot of games with this. Yeah.
Thank you.
May I ask one question as well in between? Jasche, and I see that you still have your hand up. I hope Jens has still a few more minutes.
Yeah, I found
it is totally amazing. It seems like magic. So my question then is about your initial slide about the nuisance parameters and how the Hamiltonian Monte Carlo works. Is there a limit to how linear the nuisance parameters need to be? Or have you encountered nuisance parameters where that runs into trouble? Yeah,
so that's actually where the magic comes in. So The reason why the HMC works so nicely is because we have 10 million parameters, but they are very, very similar. I mean, they are all density values, right? If you add bias parameters, other parameters, the problem can become very, very nonlinear and very nasty. So we don't solely rely on the HMC. So we basically have the block sampling approach. We use all kinds of different samplers. For very nasty parameters, which are multimodal or something like that, we use a slice sampler, because the slice sampler can, at least in 1D, still jump between the modes and has a unit acceptance rate. It's in the end, when it comes to all these meta or nuisance parameters, there's a mix of additional samplers which are actually need to be handcrafted to the specific problem. It is for this kind of problems, I think you don't get away with a black box sampler. You really have to craft it to the problem, and that's clear. As the more information about the posterior distribution you actually implement as a proposal generator into your MCMC framework, the more efficient it will be. So, and that also in turn tells you a standard black box sampler might not be the right thing for complex tasks. So you really have to tune it to the things. There's a lot of things, there's a lot of work in these things. It is not straightforward. You can't switch it on. It's not going to run like that. So it's years of work to get it there.
And I feel a bit better about my systematics issues.
Yeah, systematics are nasty. There's no easy way. Yeah.
Okay, we are already 10 minutes past the hour. Are there other questions? Jasche, did you have a second question?
Yeah, like how could the project provide any guidance on where to hunt for deviations from lambda CDM, like test the gravity, something like that?
Yeah, that is an excellent question. Actually, that is a work that we have been doing together with Harry Desmond. And Harry was interested in testing modified gravity. And one of the generic predictions of modified gravity is that there should be screening. So we would expect that gravity should behave differently in overdense regions, such as clusters or voids. And Harry basically built something which he called gravity maps for the nearby universe. And he then tested various properties of galaxies in this region to see if they are differently screened and so on. He has this, you can check several of these papers, but this is a kind of studies that we can do. In essence, what we are doing right now here during the Aquila meeting is we try to build something which we call sensitivity maps. Is the question which regions of the large scale structure respond the strongest to changes in the gravity model or in the cosmological parameter model. So the idea is then, if you find these regions which are particularly sensitive or maybe are sensitive in different ways, then you can basically take measurements at these positions and then maybe make diff estimates if things behave differently in these regions and so on. So there are various approaches. And of course, the most straightforward thing to do is you implement a modified gravity model into Borg, maybe parameterized, and then you try to estimate these parameters and see if it prefers lambda CDM or some kind of modification also. There are various ways of how you can basically test for deviations from lambda CDM.
Thanks, that's exciting.
Okay, with that, thank you so much, Jens, especially for taking time out during a collaboration meeting week.
It's fun.
Really hectic.
Yeah.
Absolutely fascinating.
Thanks.
And good luck for the rest of your meeting.